Finally, let us consider where do these supermassive black holes that power active nuclei come from. Here is a very old but still very relevant diagram produced by famous cosmologist Martin Rees about how can we generate these black holes that power quasars and other active nuclei. And remarkably, a lot of these things are still being discussed and all of them are still considered. There are some important questions to address here. First of all, where do the original seed black holes come from? Second, how do they grow? Then, what can we observe at high redshifts? And finally, how does this relate to the galaxy formation and evolution as a whole? Some of these things are still at the forefront of the modern cosmology. There are three possible mechanisms by which we can initiate seed black holes, which can then grow into the supermassive ones. The two more popular ones are that you can have stars from population 3, which you may recall are expected to be very massive, explode and generate black hole remnants, which can be in range of maybe hundreds of solar masses, and then they can grow by accretion, merging, and so on. An alternative is that you can form black hole through a direct gravitational collapse of a primordial cloud of gas and dark matter, and you start with a large black hole of thousands, maybe up to million solar masses, and let that grow. A third mechanism is collapse of a dense star cluster. We'll come to all of those in turn. There are pros and cons for each one of these models. There is also a possibility of primordial black holes that came from Big Bang through some sort of instability very early on in the universe. But those are very much hypothetical, and most cosmologists would not consider that as a likely mechanism. So whereas it's still worth considering primordial black holes, they're probably So whereas such primordial black hole seeds are still worth considering, and some serious scientists have done so, they're probably not what really happened. Certainly the most likely cause are the stellar remnants from first massive stars, population 3 stars, that we know had to exist, and if they're like massive stars we know about, they probably did collapse into black holes as they exploded. Some of them we may actually detect as they're being born through very high redshift gamma ray bursts, and people are on an active lookout for those. It is also possible that a dense star cluster, as we know stars do tend to get formed in clusters from primordial or from protostellar clouds, that clusters can dynamically evolve in a way that gravitational collapses run away and they all form, say, a black hole of thousands of solar masses. This is an astrophysically plausible mechanism, but we're not sure that it actually happens. And then, as the dense cores of galaxy potential wells form, some of them might achieve critical density and collapse into a black hole directly without even making any stars. Of course, more than one of these things can be happening. So the most plausible mechanism is the primordial star formation, population 3 stars, and that's been modeled numerically very extensively. You form high mass stars, it can be hundreds or thousands of solar masses or even more. When they explode, they leave black hole remnants, so a substantial fraction of their mass remaining. Some of them may actually form binaries, and then those merge as well. Another possibility is that you just have sufficiently dense cloud of gas and dark matter, possibly with a cuspy dark halo, and that undergoes gravitational collapse in its own. So it forms a really large black hole without even going through any star formation. This is plausible, although somewhat more speculative. Once you make the seed black hole, you have to feed it. And if it's radiating according to Eddington luminosity, you may recall that this is an exponential process and it can grow exponentially in time. So it's actually possible to achieve billion solar mass black holes by about redshift of 6. assuming you turn all the knobs in one direction, that everything goes just right. It's worth looking at the necessary energetics in a little bit more detail. So the material that is used to build these black holes would come roughly from kiloparsec distances, give or take factors of 10. And it ends with microparsec distances. So most of the mass must be radiated, of the order of 10%, as we know. However, this is done if you are dissipating only 10% of the mass of a billion solar mass black hole. That's still a lot of mc squared, and it adds to of the order of 10 to the 61 ergs. And you have to emit that over a period of time that's maybe 700 million years, from the formation of the very first stars down about redshift of 6 or 6.5, which means there is going to be a really luminous object. It's good because then we can hope to detect them. And this would be something like 10 to the 13 solar luminosities, as much as most luminous quasars that we know. The interesting thing is that forming such black holes could actually contribute substantially to the reionization. We said that most of the reionization, maybe all of it, is due to young stars, hot, massive, really bright, population 3 stars. But formation and early growth of black holes can be an important contributor. So here is the challenge. If we take the concordance cosmology, redshift 30, which is about as early as you can start making stars, the universe is about 100 million years old. By about redshift 6, 6.5, it's of the order of 900 million years old. So you have about 700 million years to do it. Suppose you want to make a billion solar mass black hole, and actually those that power the most luminous quasars at these redshifts may be even 10 billion solar masses, but let's take billion solar masses. Suppose you start with a seed mass of 10 solar masses, say black hole remnant of one of the POP3 stars. So that means that you need to go through 8 orders of magnitude of growth, or about 18 e-folding times. If you start with a 100 solar mass black hole, about as massive as plausible for stellar remnant, then only 16 e-folding times. Well, there is a Salpeter timescale, which is e-folding timescale corresponding to exponential growth of accreting black holes that are accreting at Eddington luminosity. That turns out to be of the order of 40 or 50 million years for an efficiency factor of 0.1, which is what we've been assuming. So you can just barely fit that, and that means that you are always radiating at Eddington luminosity. There is an abundant supply of fuel, and there are no disruptions. Everything has to go right. So even though supplying mass may be challenging by itself, that's actually probably not the worst problem. The worst problem is probably getting rid of the angular momentum of the fuel that gets to be absorbed. Once you have black holes, they will accrete material, right? But they can also merge. Since there'll be one of these in core of every massive galaxy, galaxies keep merging, structure forms hierarchically. Eventually, black holes will start merging too. And this growth by merging is probably just as important for black holes as it is for host galaxies. Note, however, that this simply means the mass that's already collapsed in black holes is being rearranged. It does not involve any dissipation of energy. All of the dissipation, all of the luminosity comes from the accretion process. And there are now excellent numerical simulations of black hole mergers, and the hope is to detect these events through gravitational wave astronomy, which is now just beginning with the LIGO Observatory and its successors. We know that such things do happen. At low redshifts, we've seen very close double active galactic nuclei. We see double active galactic nuclei at a broad range of redshifts, but here are a couple of nearby examples. The one is dual radio source. We can see the jets are actually being distorted. The other one is a double X-ray source in a nearby galaxy. These are still too far apart. It'll probably take many millions, if not hundreds of millions of years for these to merge. But there could be many more closer pairs that are relatively unresolved. And one interesting thing is that aside from predicted gravitational waves, what will be electromagnetic signatures of such supermassive black hole mergers? There's been a lot of theoretical discussion of this, and as of now, it's not really clear what, if any, will be the observable signature, but we can hope to detect them someday and thus see the assembly of supermassive black holes in action directly. And that completes our class. I hope you found it interesting and you learned a few things about cosmology. Thank you.